welcome back to the lecture series of finite volume, and what will continue our discussion where we left in the last lecture. So, in addition to psi r greater than 0, a condition is also imposed that psi r whereby psi r 0 for negative values of r. So, now this condition will be satisfied if psi r less than equals to 2 and psi r less than equals to 2 r. So, combining all of this to produce a TBD scheme, a criteria similar to that CVC or CBC can be developed, where one can write psi r equals to mean of 2r and 2 when r greater than 0 and 0 when r less than equals to 0. So, that is the condition that one can devise, and this condition can be seen in the psi r diagram. This is called the psi r diagram, and this is the region which is TBD monotonicity region, where it is satisfied. This is also called Swebe diagram. So, this satisfied this criteria of psi r equals to mean of 2r and 2 and 0 where r greater than 0 and r less than 0. So, these are the zone which is TBD monotonicities. So, if you look at this, the simply you can grasp the formulation of TBD scheme. Any flux limiter psi r which is which lies within the TBD monotonicity region will yield an TBD scheme, or this diagram is very similar to that NVD diagram, normalized variable diagram, that we discussed earlier. Now, the limiters for all these schemes presented so far can be derived, and their functional relationship can be also drawn on this particular diagram. For let us say very specifically limiter of central difference scheme can be easily obtained, where psi r f for CD scheme would be 1, while same thing for second order upwind scheme can be computed as phi f equals to phi c plus half s r f phi d minus phi c, which is 3/2 phi c minus half phi u. So, which gets you back for second order upwind, it is phi c minus phi u divided by phi d minus phi c, nothing but r f. So, this can be displaced here. This is the diagram, so which shows the limiters for second order upwind and CD in this psi r diagram. So, one can see that psi, if from this diagram you can notice, if psi r f equals 0 for r f less than 0. So, r f less than 0, psi r f is 0, the second order accuracy is actually lost at extrema of the solution. Now, both these second order upwind and CD, they are actually by nature second order scheme and accurate, and which can see clearly pass through the point 1 1. Both this and this but neither the downwind scheme or upwind scheme pass through this point. So, also one can, so thus it is very clear that the scheme to be a second order accurate, it has to pass through this coordinate 1 1, and the limiter should lie in the region which is bordered by second order upwind and the CD scheme. So, the all the scheme which has to pass through or which is supposed to pass through 1 1 and lie within this border, they will be of second order accurate. And so, the corresponding region one can show in the NVD. So, if you look at, this is the region on normalized variable diagram. So, here we are trying to make a one-to-one correspondence between NVD and the psi r diagram, because psi r diagram is going to get you the TBD different class or variant of TBD scheme. Now, here if you put the monotonicity region on a for a second order scheme lies in this shaded region, which is bounded between the CD and the SO. So, this is the zone which is actually going to be the second order accurate scheme, or that will provide the second order accurate scheme. Now, once we adopting this approach and the procedure which we followed for the second order upwind scheme, the functional relationship of the limiters for any higher order scheme can be formulated. For example, this is the higher order schemes functional relationship. So, we can say upwind scheme, the psi RF is 0. Now, for downwind scheme, psi RF equals to 2, and then we see this, we can see these things in the psi RF diagram here, which nicely shows the, this is the region where all the monotonicity preserving scheme can be found in this particular shaded region, and this is the psi R diagram for higher order scheme and TBD monotonicity preserving scheme. So, here if you get, as we said, the upwind scheme will provide you psi RF equals to 0, that is the upwind scheme which lies here. Now, for downwind scheme, the psi RF is 2, which is lying there, this is the constant line. Then from scheme, the psi RF is half of RF by 2. So, that is what the from scheme. Second order upwind, so psi RF is RF. So, that pass through the 0 0 and 1 1. Then CD, where psi RF is 1, that is where it is constant, and then you have quick, which is psi RF equals to 3 plus RF by 4. So, this is the line for quick. Now, the from scheme is essentially the average of CD and second order upwind scheme, and its function relationship can be presented like phi f equals to half of phi c plus phi d by 2 plus 3 by 2 phi c minus phi u by 2, which is nothing but phi c plus phi d minus phi u by 4, and phi f equals to phi c plus half psi r f phi d minus phi c, which leads to that psi r f equals to 1 plus r f by 2. That is what you get. Now, all these are shown here. So, the limiting psi r f of various schemes are also given, and the schemes which pass through this and lie within the shaded region, they will give you different kind of higher order TBD based scheme. Now, another thing is that many TBD scheme which are there available in the literature, the limiters for a number of them we can see, and the functional relationship of their limiters can be also presented. So, here we can see some of these limiters like mean mode limiter, Usher limiter, Marshall limiter. So, these are all shown in the psi r diagram. So, these are limiters in psi r diagram. So, this is what it shows. Now, how one can actually get this functional form for all this? So, for let us say we start with the mean mode limiter. For mean mode limiter, psi r f is between maximum of 0, minimum of 1 and 2 r f, comma minimum of 2 and r f. So, that is how it takes. So, it is the maximum of one of these three, and there either it could be minimum on 1 or 2 r f or minimum of 2 and r f. So, that is where the mean mode limiter is picked up. Then similarly, Usher limiters. Usher, the psi r f is maximum of 0, minimum of 2 and r f. So, it is taken the 0 and the minimum between 2 and r f. If you look at the Marshall, so Marshall it is psi r f equals to max of 0, minimum of 2 r f, comma r f plus 1 by 2, comma 2. So, this is between 3 parameters. That is how the Marshall limiters work, and in between that there would be Van Leer limiter. So, the Van Leer limiter, which is very popular limiter in the high speed flows or the compressible formulations, this is used. So, that is Van Leer, and then Super B. Super B, which is psi r f equals to max of 0, minimum of 1 2 r f, minimum of 2 comma r f. So, this is how one can define these limiters, and they are presented in this diagram. So, these are the preserving calculations for this. So, all these are the shaded regions here, these are going to provide the TBD kind of scheme. This, then here this, so this, all these shaded regions are going to provide the TBD based scheme. Now, so once you find out this psi r relationship, and one can actually form this higher order TBD based scheme which are going to be monotonicity preserving, and we have seen what are the limiters for that. Now, the second is that we can find out the NBF and TBD relation, which is going to be very important, so that both NBF and TBD formulation, what it offers is that the one unique thing is boundedness. So, through different ways. So, now one can achieve this relationship by first deriving a relation between RF and normalized phi tilde, then we can compare between NBF and CBC with the TBD CBC, and then finally can find out the general transformation that allows the functional relationship of any TBD schemes to be written in NBF. So, that will allow to write that down. First we need to find out this, then use the information of NBM CBC relationship along with the information of TBD CBC, we can actually find out this information. Now, so how we proceed about that? To proceed, first we need to find out the relationship between RF and phi c tilde. So, the definition of RF says it is the ratio between two consecutive gradients, which is phi d minus phi c. Now, one can write that phi c minus phi u divided by phi d minus phi u, and denominator you can have phi d, phi u plus phi u minus phi c. So, what it does, it just divide by both numerator and denominator by phi d minus phi u, which will cancel out, and also this phi d minus phi c you add phi u and then subtract the same amount. So, it is a algebraic manipulation which will lead to phi c tilde by 1 minus phi c tilde. So, that essentially provides phi c tilde equals to RF by 1 plus RF. So, that is the relationship that one can obtain between phi c tilde and RF. Now, using this information of linear scheme, one can be compared in two different frameworks. So, the limiter psi RF equals to 0, which actually represents the upwind scheme in TBD formulation, is also equivalent to the upwind scheme, also equivalent to the upwind scheme in NBF formulation. So, that is where, that means this will tell you phi f tilde is equal to phi c. So, this follows the fact that psi RF equals to 0, that means phi f equals to phi u, which in other way round phi f tilde is phi c tilde. So, the upwind scheme is imposed as a limit for the TBD CBC when RF is less than 0, and the similar or equivalent condition in NVF CBC. So, this is the condition for the TBD CBC and this is the condition in NVF CBC is RF less than equals to 0. So, that tells us phi c tilde 1 my phi c tilde less than 0, that is phi c tilde less than 0 or phi c tilde greater than 1. So, these also represent the condition for imposing upwind scheme in the NVF CBC. Now, in addition to that, on NVF CBC, the functional relationship has to increase monotonically in the region where, so the monotonically increasing functional relationship has to satisfy this condition, phi c tilde lies between 0 to 1. So, now if you recall your psi r diagram, this extends the region in psi r diagram like RF goes to plus infinity and it is between 0. So, this is the condition you get in psi r diagram. So, now the phi c tilde tends to 1, which will get you RF equals to phi c tilde by 1 minus phi c tilde, which tends to infinity or positive infinity. Now, further you have this TBD CBC condition, which is psi RF less than equals to 2. So, the psi RF less than equals to 2, it is in TBD CBC. This equivalent condition in NVF CBC would be psi RF equals to 2, which will get you back phi f equals to phi c plus half psi RF into phi d minus phi c. That means phi f equals to phi c plus phi d minus phi c, which means phi f tilde is 1. So, psi RF less than equals to 2 gets you back in NBD CBC less than equals to 1. So, whatever the functional or the conditions here in the TBD CBC, equivalent conditions one can find out in NVF CBC. Now, if this condition is satisfied in TBD scheme, this condition needs to be satisfied in NVF conditions. So, the last condition which is imposed on the TBD CBC is that psi RF less than 2 RF. Then the equivalent condition here one can find out equals to 2 RF. Now, phi f equals to phi c plus psi r f by 2 into phi d minus phi c. So, that will get you phi c minus phi c by phi u, phi d minus phi u multiplied by phi d minus phi c, that is 2 phi c minus phi u. Now, that is what you get, phi f minus phi u equals to 2 phi c minus 2 phi u. It is an algebraic calculation, and that get you phi f tilde equals to 2 phi c tilde. So, the condition which will satisfy it here, psi r f less than 2 r f, the equivalent condition is phi f tilde equals to 2 phi c. So, this is slightly more restrictive than the NBF CBC and is only difference between two formulation. Now, based on this condition, the TBD CBC and the modified, so TBD CBC and the modified NBF CBC would look and can be seen in this particular diagram. So, this is the condition, and we have imposed all these conditions of the TBD CBC one by one, like psi r f less than 2 r f, that is one condition in TBD CBC. So, equivalent condition NBF CBC is phi f. When the psi r f less than 2, the equivalent condition gets phi f tilde less than 1, and previously we have got r f less than equals to 0 or r f less than 0, then this is what you get, or TBD NBF CBC get you this information. So, there are conditions or equivalent conditions between the TBD CBC and NBF CBC. So, you got three different conditions here. One is this condition, this is one, then you get the information of this, and then you impose TBD CBC this condition, equivalent condition in NBF CBC, then we have imposed other TBD CBC condition and equivalent conditions in the NBF CBC. Now, we can see how this different mapping or one-to-one mapping can be plotted in the diagram, and that we will see in the next lecture, and we will stop here today and continue from there. Thank you.